everybody. Okay, so we are going to go through our lab, which is this one titled, what's the title? Types of Chemical Reactions, right? I'm going to go through this entire front page with you guys, including these demonstrations down here. This up here is note-taking. Please write down everything I talk about and write down everything I write when we do this area as well. And then when we do these teacher demonstrations, I am going to show you guys how to fill out the backside for your lab. Okay, here we go. So the first one is we're doing a test to test for gases. And we want to see what kind of gas we're producing. And so for this example, what we need is some zinc. And so I have put some zinc in this test tube here. And we also need some hydrochloric acid. So I'm going to pour some hydrochloric acid in with this zinc. And you can see right away, there's bubbles forming. Lots and lots of bubbles, okay? So I'm gonna get a splint ready. And I'm gonna put it next to the test tube. Did you hear that? Okay, let's try it again. Okay, I wanna actually make some more gas. Oh, it's actually burning. Can you see the flame right there?
The camera can't, but I can see it.
Okay, so I'm going to see if I can make that flame go away now. Okay, the flame went away. I want to try to test the gas again. So I'm going to let the gas build up. Okay, so did you hear the sound?
I heard it. I
Okay.
believe the camera caught it. So
Okay, we'll try it one more time. See if we can get that sound. All right. I'm just trying to trap gas in there as much as possible as this gas is being generated. There, that sound was much better. So as you guys could hear, hopefully you could hear, there's a pop. And sometimes the pop is actually a little bit louder and there could be a bark, so it goes pop. It totally depends. I'm making stupid faces, aren't I?
no.
So, but that's the thing that we're going to look at. So if you go to our piece of paper here, all right, so what we did is we took zinc and we reacted it with hydrochloric acid. So when you look at the ingredients over here, our reactants, you can see how the only gas we can really make out of these elements would not be oxygen or carbon dioxide, but can be hydrogen gas. Now there's some other products here, but we don't really care about those right now. This is what we're focusing on. So I'm not going to write a complete balanced equation. But the big deal with this one is that it pops. Oops, I think I spelled that wrong.
That's
didn't I?
okay.
Pops. It pops. It makes a bark sound if there's a lot of gas there. Okay? So that's the thing we want to have when you do a splint test and what you have happening is a popping sound, or you might see the flame, like, I'm not sure if you guys saw it on my video here, or a barking sound. That means hydrogen gas was produced, okay? All right, the next test that we're going to do has us testing if oxygen is formed. So in this beaker, I have hydrogen peroxide, and what I'm going to add to that is something called manganese dioxide, which I have on the spoon right here. I want to get my flames ready to go. Okay, so when I sprinkle this in, see how the gas is starting to form bubbles? Now, if you look at the splint, it's not even burning, but when I put it next to this, what happened to it? It relit, right? And it relit because the gas that's being produced is oxygen gas. Is that cool?
That was really cool.
Okay. All right, so let's make that go out. So in this one, hydrogen peroxide is this formula. And the manganese dioxide is actually not a reactant. It's a catalyst. And that means the manganese dioxide gets written over the arrow because it doesn't get used up in the reaction. When I'm all done with this, I can filter that manganese dioxide out and reuse it again and again and again. So it never gets used in this whole reaction. But what it does is it breaks this apart, and what we're testing for is the oxygen gas. And there's more, but again, I don't care what the more is. What we care about is this. And what this does is it relights a glowing splint. All right. It can also make a burning, burning, I'm totally spelling this wrong.
That's okay.
B-U-R-N, burning splint brighter. Okay? So that's the information we want to gather for that one. All right. So our third one that we're going to look at has us forming a gas. But in order to do that, we need to use vinegar. So in this beaker, I already have some vinegar. And we also need some baking soda. So I want to get my splints going again. So we're ready to run the test. Notice how in every one of these, when I'm doing the splint test, I have my splints ready to go in order to test what I need to test, right? And if you notice, I always have 2 splints ready, so I always have a backup, okay? So I'm going to put my baking soda, and again, you see bubbles, right? When I put this splint next to it, it goes out. Again, it goes out. I'm not even putting it near the liquid, so you know I can't be getting it wet. So this gas is making the flames extinguish. All right? All right. So for this one, what we have going on is baking soda is sodium bicarbonate, and vinegar is acetic acid, HCH3COO. All right, so there's a lot of atoms here to work with, and so we're not going to talk about all the other products one can make, but notice there's enough atoms in here to make the carbon dioxide that we're looking for. And that's the gas that puts the flame out. Okay? So, when you do your lab, and one of the procedures specifically says that you're supposed to do a splint test, then make sure you have your splints ready like I did, right? And then you run your test, and then you're going to look, do I have an explosion, a pop sound? Do I have something that makes it glow brighter or start glowing or start burning better? Or do I have something that makes the flame go out? And then I know it's one of those 3 gases. If the test never says to do a splint test, then don't. You didn't make a gas. Don't do a splint test unless the directions tell you to do so, okay? Now, there's another test that you'll be doing when the directions tell you to do so, and that is using litmus paper. All right? So, you'll see right here, this is litmus paper. And when you do it, you have to use both the red and the blue together. So in this case, you can see I have both a red and a blue piece. And this is an acid. It's nitric acid. It's not a strong nitric acid, but it's acid. And when I put this acid on the 2 pieces of paper, notice that both of them turned what color?
Do you want me to answer?
No, I'm not letting them yell it out. Hopefully they did. They like, red! Okay, awesome. So if the red and the blue both turn red, what you have is an acid. Red acid. I like using mnemonic sounds. Is that what it's called? Mnemonic things? Okay, whatever. But what you have is an acid. Now, acids always have a very specific formula, and that's what I wrote right here. Okay? The H means you have an H plus ion, and the X means that you have some kind of a negative ion. In the case what I had right here, I have my hydrogen with a nitrate that I was using. So this is my formula HX because I have a hydrogen with some kind of a negative ion. All right? So I was using HNO3, and so this is that H out of this, and the NO3 is the X out of this. And when you test your products, if everything turns red and you think you have an acid, then you know your basic formula for your product will have to have these 2 things in it, a hydrogen ion and some negative ion that comes together. All right? So right here, I have a base. I have to put some into the cup. That when I put the 2 pieces of litmus paper in there, what happened to both of them? Again, I'm going to wait for them to yell, "It's blue!" Yes. If red and blue both turn blue, oh, I got to put turn in there. Turn blue. Blue means you have a base. Okay? When everything turns blue, you have a base. And bases have this basic formula right here, where M is your metal. It's your positive ion that you have. And then with that is an OH, right? And that's your hydroxide. So whenever you have a base forming, you have some kind of metal that is with a hydroxide together. So this is an example of one, or today I use the KOH. So in this case, the M, the metal, is my K, and then the OH is the OH part of this. Okay? And then the last one I have is when you have something that is neutral. When you put the 2 papers in, they don't change. Notice how the red stayed red and the blue stayed blue. There's no change with this. You will never have this one turn blue and this one turn red at the same time, because this turning blue means base. This turning red means acid. You can't have an acid and a base at the same time. You can have something neutral and they stay the same. So if red stays and blue stays, you have something that is neutral. Okay? And whenever you have something that's neutral, it's going to use this basic formula where M is your metal and X is your negative ion. So I could have used water for this one, but today I used potassium iodide because that's my metal and that's my negative ion that I put together. Now, not only could I use water, but I could also use spit. Ta-da! My spit is neutral, right? Okay? So, that is the note-taking part. And everything you did with the litmus paper and everything we did with the splint test, these are going to be things that we will use when we do our actual tests in lab. Now remember, you won't use splint tests every single time, and you won't use litmus paper every single time, but these are some really good ways to help you predict your products. So let's do some examples, okay? So the first procedure that we have here tells us that we need to have some isopropyl alcohol in an evaporating dish. So here's my evaporating dish, and there's some isopropyl alcohol in there. All right, I need to ignite this. So I'm going to make sure my fingers are far enough away from this when I ignite it. Okay, not only do I need to ignite it, but then I have to hold a watch glass with some tongs above the flame, and I want to look for something that's happening. Okay, so there's my flame. So here's my watch glass. I'm going to hold it over the top, and there's fog forming. I don't know if everybody can see that. So I'm going to do it a second time. Okay, it's fleeting. There, fog, and then it goes away because it gets really warm. Okay, so if this was my lab paper, when I look at this, it tells me result. It tells me to look for something happening. So I saw burning. Okay, burning that occurred in the evaporating dish. Okay, I saw fog form on the watch glass. All right, so this is all my data, and I'm going to use this to help me figure out what was going on. All right, so I know this was my ingredient. This is something I was using, so I call that my reactant. All right, that's what I'm going to do over here, is start filling this in, but I don't want to write it on the back side yet because I want to make sure I write it neatly. So I'm going to figure things out over on this side first, and then I'm going to transfer it over. So I know I had C3H7OH as a reactant. This is my alcohol that I was using, right? And when you look inside the container, it's a liquid. So I'm going to show that it's a liquid, all right? And this was burning. And as you have seen with reactions that burn, this must be some specific reaction, all right? Think about those reaction types we were just talking about yesterday. Think about the ones that show burning. There's another reactant that is a part of this. That reactant is oxygen gas and is diatomic. So notice I'm putting down gas. All right, if we have this burning and we have this fog forming and we recognize that we only have carbon, hydrogen, and oxygen atoms available, right? Our question that we should be asking ourselves is what would be our products? Okay, what products would we be forming? What thing could be a fog that forms on a watch glass that dissipates very quickly after it's heated? What particles could we make from carbon, hydrogen, and oxygen? And what kind of a reaction is a burning reaction? And my filmer here is about ready to burst, wanting to know the answer. Oh, you know the answer already, don't you? It's going to be carbon dioxide as a gas and water as a gas. Because that was the stuff that was the fog on our watch glass. Okay? Now this is not even balanced yet, so I'm going to do that balancing over on the other side. But now I know these are my reactants because I had burning going on, and because I saw the fog and I know something about this kind of a reaction, that these must be my products that I formed. So C3H7OH as a liquid with oxygen as a gas formed carbon dioxide as a gas and water as a gas. I did leave a little bit of space in front of each of my reactants and products, well, not in front of this one, in order for me to put coefficients in for balancing it. All right. So for balancing this, if I had my pencil, I would do this first in pencil, but I'm going to do it in pen, and so I have to scribble. Please accept the fact that I might have to scribble. So there's 3 carbons here. So I'm going to put a 3 in front to have 3 carbons. I have 7 plus another one here for a total of 8 hydrogens. So if I put a 4 here, I'll have 8 hydrogens. This gives me 6 oxygens, 3 times 2 is 6, and 4 oxygens, which is 10. And there's no way I can do this plus add 1 more and have 10. That's never going to balance. Okay? So because that's never going to balance, that means that this number here has to be greater than this. I need to make this oxygen an even number, so I'm going to have to put a coefficient of 2 in front of this, which changes my carbon count now to 6. See why pencil is so good to use? Changes this 8 hydrogens to twice as many hydrogens, so I now have 16. So I have to have 16 hydrogens. So this number is going to have to be changed to an 8. So I have 16. And now I have 12 oxygens right here. And I have 6 oxygens. So 12 plus 6 is 18. No, I don't want to put a 9 here for 18 because remember, there's still 2 oxygens that are right here. All right, so 12 plus 8. 12 plus 8 is not 18. 12 plus 8 is 20.
What?
12 plus 8 is 20.
Oh, okay.
Yeah, because this is 12, and that's 8. That's going to be 20.
You didn't say 8 the first time, Mom. You said 6.
Oh, did I say 6? Okay,
Yeah.
sorry. So, yeah.
So my math was right. You just
Said
it's
wrong
fine,
numbers.
It's fine. It's
Okay,
cool.
okay. So we got 20. So no, you can't just put a 10 here because you also have 2 oxygens here. So a 9 times 2 will give you 18, plus the 2 more here will give you 20. So now this is balanced, right? And we should recognize the reaction type right here is a combustion, because I want you to start realizing reaction types, whether they're single replacement, double replacement, synthesis, decomposition, or combustion. Combustion that we learned about always end in carbon dioxide and water, always have burning going on in which one of your reactants is filled with carbon, hydrogen, or even oxygen part of it, and it burns in oxygen, burns in the air. So how did we know this is what we made? The fog on the watch glass is what we assume was our water. Okay? So that's how you fill that part of that sheet out. So now we're going to take a look at our next one. Okay? The next one tells us to take copper metal. I could also do it with magnesium, but I'm going to do copper. I'm going to strongly heat it for about 30 seconds. And then I want to take a look at any changes in the appearance. All right, so over here, I have a Bunsen burner going. Here's my copper. Take a good look at how it looks, okay? It's got the beautiful copper color. It's shiny, right? If you look at this when I put it in my hands, it's like little, it looks like it compresses in there, right? And if you look at my hands, there's nothing left behind on my fingers because it's pure copper. All right, let us heat this. Ooh, pretty color flame. Do you see the green in the flame? So we're gonna do this for about 30 seconds. That flame is gorgeous.
It is.
Makes me think of St. Patty's Day, which was just a couple days ago. Yesterday. But by the time they see this, it'll be 2 days ago. All right, so if we take a look at this copper, definitely not the shiny color we had before. All right, I'm gonna bring my hand to it closely because I don't want to burn myself. Okay, I'm gonna set this on a watch glass. All right, so if you take a look really closely where the tongs were holding on to the copper, you can see that's copper that was not changed because the tongs were blocking the flame from getting there and any other material from getting it. But then if you look at this part where the flames had total access, it's different, all right? When I touch it, there's pieces that are breaking off. I gotta put it over here. There's little dusty pieces that are breaking off in the watch glass. And then I also get some on my fingertips, but it seems to wipe away. Okay? So you see little dusty pieces on my fingertips? My fingers look dirty. Okay? So this black material formed. All right? So all we had was copper, and we did something to it by heating it, and there has to be something else that went with the copper for us to form the material at the end. All right. Now with this particular one, I don't have a test for you guys to determine what formed. All right. This would be one that you wouldn't do in lab because there's nothing for you guys to figure out what happened. But we do know that it turned black. And if you happen to be a person knowledgeable in chemistry like me, this black means that your copper actually turned to copper oxide. All right. So we really formed copper 2 oxide. And it was still a solid, just like the original copper we started with was a solid. So what must have been the thing that reacted with the copper? Okay, that would have been the oxygen that's from the air. So copper plus oxygen from the air, when heated, forms copper oxide. That's a solid. All right, now I'm going to fill that in on this side. So copper as a solid reacts with oxygen from the air and is heated, and it forms copper oxide also as a solid. You can see that this is not balanced. This has 2 oxygens where this one only has 1. So a coefficient of 2 will go in front to balance it. That means I have 2 coppers, and so I have to put a 2 here to show 2 coppers. So this shows my balanced equation of what happened. My evidence I had was that copper turned black, and because of my knowledge of chemistry, I know that meant I formed copper oxide. you guys will be doing tests or making some other kind of conclusions. And when you look at this kind of reaction, the fact that all we had was this copper in the air making this one product, that would be a synthesis reaction. All right, last one we're gonna do. I'm gonna go over here. With this last one, I have, some of you guys actually saw this today in class. And we didn't do a finished test with this in class, but we did talk about it because when I cut the sodium, I told you it cut like summer butter. Remember? Those of you who were in class yesterday. So that sodium is the silver metal that when I expose it to the air, it's going to start dulling. But I'm going to put this in water. Okay. Now, if this doesn't do what it's supposed to do on its own, I'm going to try to prompt it with a flame. But today in class, one of my classes automatically started on fire on its own, and the other class, it didn't. So let's see if I can get it to start. There. See how that pop happened? And that burning that's happening right from that piece of metal? Okay? That's giving us an indication of what kind of gas was formed. Right? Flame, and it popped. You should be thinking about what kind of gas that is. All right? The other thing we're going to do with this one is we're also going to do a litmus test, but I can't do it until that little piece stops moving around in there. So I'm going to come back to this. Okay, so I had distilled water, and water is H2O, and it's a liquid. And to that, I added a piece of sodium. Sodium is Na, and that was a solid. When I had the splint near it, it popped. Okay, so that's my result for this one. Also, after the reaction stops, I'm going to use litmus paper. So I'm going to use my red and blue litmus paper. And what color did my litmus paper turn? Okay, so I'm going to write that down right here. Result is that red and blue turned blue. And when things turn blue, it means I have a base. Okay? So these two things are going to tell me what I need to do with my reactants and my formula. So that if something popped, these are my atoms I have to work with. I had to have formed hydrogen gas. If a base formed, let's go back up here. If a base formed, I have to have a metal and a hydroxide that came together. So my only metal I have here is sodium. Sodium is a +1 charged metal. Hydroxide is a -1. So when I take a +1 sodium and a -1 hydroxide, that is going to be the formula for my product. And then because this is mixed with water in here, I'm going to say that this is aqueous because I know all the water didn't get used up. Okay? So there is my equation, and now I want to rewrite that on the other side. Okay? So I took water as a liquid, and to that I added sodium as a solid. All right? I'm not going to do anything with flame or anything like that because the splint test was only used to test for my products. One of the products that I tested for was hydrogen. It was a gas. And the other one was the base of sodium hydroxide, which I said would be aqueous. All right, so balancing this, you can see I have 2 + 1 is 3 hydrogens over here, right? And this is only 2. So this is always going to be an even number, and as long as there's a 1 or a 3 over this, this is going to be an odd number. So I'm going to put a 2 in front. So I have 2 hydrogens plus these 2 hydrogens is 4 hydrogens. So I can put a 2 in front of here, and I also have 4 hydrogens. So 2 + 2 is 4, and then this is 4. This also means I have 2 oxygens, and this 2 means I also have 2 oxygens. So that's balanced. The 2 sodiums, I need to put a 2 in front of here to show 2 sodiums. All right? So how did I know I formed hydrogen gas and sodium hydroxide? Well, splint test popped, which means I have hydrogen gas. And the red and the blue litmus paper turned blue, which means I have a base. So these two things totally helped me out in writing the formulas for my two products. And if you then look at the whole equation, we have this compound reacting with an element, forming an element, and yet another compound. And so you should recognize this as a single replacement. All right? So when you turn and go to the front inside of your lab, you will be doing all of this on Wednesday and Thursday, running these labs with me. And while you run your labs, you're going to be doing what I did and eventually filling out the back side. Notice my back side looks a little bit messy because I made mistakes balancing it because I was using ink, not pencil, right? But overall, I wrote this only after figuring things out on the front side. All right? So, hopefully everything that I wrote down in here, you guys wrote down as well. And I will see you on Wednesday, and we will get started on this lab.